Okay, well, good morning, everybody. Is that me dinging? All right, so again, good morning. If anybody didn't pick up their homework last time, they're just in the folder up here at front. New homework assignment for the week. Of course, these are for the entire week, due next Wednesday. I might also note that you do have a midterm exam, your second midterm, coming up a week from Friday. And it could cover anything through this week's homework set. So anything through these problems in Chapter 14 are fair game on next Friday's midterm. And we'll talk more about the midterm later in the week or no later than next Monday. I suspect the format's going to be the same as the previous exam, so you can certainly start getting your note cards ready. And it'll begin with material that was not part of the first exam. So basically starting on section 10.4, which is ranking cycles, right through 14.3, which is what we'll cover this week. So anyway, just be prepared. So we're done now with our discussions of thermodynamic property relations. And now we're going to move on to the next topic, which is mixtures. Now, just so we're all aware of what we're going to be discussing, we would note that since we're talking about mixtures, clearly we're not talking about pure substances anymore, right? We could have a mixture of multiple substances within our mixtures. Sometimes we only have two, sometimes we have many more than two. But we're certainly going to be dealing with mixtures and not pure substances anymore. This is going to be necessary for us as we start to analyze air conditioning and air-water vapor mixture processes. It's also going to be important for us as we begin to look at combustion processes, which will be like the last topic we cover in this class. We certainly need to have an understanding of mixtures before we can go into those topics. Also, cooling towers. I've mentioned cooling towers several times over the course of, this course in thermodynamics. Perhaps we have a basic understanding of what a cooling tower is. It's just a way of transferring heat from a water stream into the air. But still, we need to understand the nature of mixtures. Keep in mind that the air that's around us is not a pure substance, right? I mean, we know, first of all, that it's a mixture of oxygen and nitrogen, but it's also also include a lot of water vapor, right? I mean, there's water vapor in the air. Sometimes the air is drier than other times, but still, it's air-water vapor mixtures that we're really going to be dealing with. And again, this is material that we'll get into over the next several weeks. So I suppose the first thing that we should do is just talk about some of the basics. And even before we talk about the basics, let me just note that we're only going to be dealing with gases. Okay, so we're only going to be dealing with gases as we deal with mixtures. And furthermore, we're only going to be dealing with ideal gases. Okay, so certainly one could analyze mixtures using real gas relationships, but it's a little more complex than we really need for this particular class. So we're just going to assume that whatever mixtures we have are indeed ideal gases, and just be aware of that. Another thing I might note is that there's really two broad categories of analysis that we're interested in. Okay, one type of analysis we would call gravimetric. And gravimetric analysis is basically mass analysis. However, in other problems, we're going to be interested not in the mass of the material that we're analyzing, but we're going to be interested in the number of moles. So we may also be interested in molar analysis. So the other one is just called molar analysis. And certainly as we analyze mixtures, in some problems we're going to have to do a little bit of both. I mean, sometimes we're interested in mass data, sometimes we're interested in molar data. But nonetheless, there's these two broad categories that we should be aware of. You'll see this described in the textbook. Nonetheless, what I'd like to do is just start with lots of new terminology, lots of new notation, and just get us all prepared for this whole topic. By the way, one could certainly put together thermodynamic property tables of mixtures if you wanted to, but there's just such a vast array of mixtures. Even if we just think of, say, an air-water vapor mixture, even within that category, you could have dry air, relatively humid air, quite humid air, anything in between. So it doesn't really make a lot of sense for us to put together what would amount to be thousands and thousands of thermodynamic property tables for all possible mixtures. The better thing to do is just to use the property data for pure substances like water or water vapor, and for each of these substances that's in a mixture, somehow combine the data that we already have so that it will be applicable for the mixture. So that's our general approach. We're trying to come up with a variety of equations here so that we can properly relate the different components within our mixture. So for now, the first thing we're going to do is just, again, go through all sorts of terminology and notation. So we're going to be analyzing mixtures. And when we talk about a mixture, we're typically going to use a subscript M. Okay, so M simply deals with mixture. And then we're also going to have individual components. So a mixture is basically made of its components. And when we're talking about an individual component, then we're typically going to use a subscript I. Okay, so the mixture itself, whatever we're dealing with, whether it's its mass, its number of moles, its internal energy, it doesn't matter. If we're talking about a mixture, though, we'll use a subscript M. And if we're talking about a particular component, we'll just use the subscript I. Now keep in mind that for some mixtures, as we start looking at real problems, then we're not going to use the subscript I. We'll just use a subscript that corresponds to the chemical species that we're analyzing. So if it's water, we'll just use the subscript H2O. If it's refrigerant, we'll just use R134A. If it's oxygen, we'll just use O2 or whatever. So when I'm generating the equations, I'm just going to put them in terms of some individual component I. But again, when you're doing real problems, you use the chemical symbol that's appropriate. Now, with this in mind, first, we're often interested in the mass fraction of a particular component. So mass fraction, we're just going to use MF as mass fraction. And if we have a particular component I, which is, of course, what we have the mass fractions of, and then we'll just put the appropriate subscript. So, for instance, MF with the subscript I is really just the mass of component I divided by the total mass of the mixture. So I'll just call this mixture mass. Okay. In other words, the mass fraction is just going to be M sub I over M sub M. Now, please note here that the subscript M clearly is not the same as the variable M, right? This M here refers to the mass, right? The subscript refers to the mixture or the individual component. Right, so mass fractions is something that we're going to be calculating for our different processes or for our different mixtures. But we also have mole fractions. And the mole fraction just uses the letter Y. So if we have a particular component, let's call it component I, then the mass fraction of that component is really just the number of moles of component I divided by the number of moles of the mixture. Okay. So in other words, we know from previous discussions that we just use a capital letter N to represent the number of moles, or the mole number, if you will. So N sub I represents the number of moles of that particular component I. And of course, N sub M would represent the number of moles of the mixture. Okay? And again, over here, m equals mass, not the subscript. And over here, n equals the number of moles. So again, just keep track of all this. Of course, we might also want to note that because we're dealing with fractions here, if one were to sum the fractions together for all the different components, then it would have to equal that of the mixture. So for instance, the mass of the mixture has got to be the sum over all components I of the mass of each individual component. So this is something that should make sense. Similarly, we would note that the number of moles of the mixture is going to have to be the sum of the number of moles of each of the components I. So we'll just sum, again, overall I. I'm not going to keep writing the word I equals components. I think we just understand that I represents an individual component. Nonetheless, this would then be the sum of all the moles of each of the individual components. Okay. Keep in mind that the number of moles is just an equivalent number of molar masses. I mean, we've talked about this before. You've seen this going back to chemistry classes, right? If you have water, we know the molar mass is 18. Well, if you have 18 pounds of water, then that's 1 mole, right? If you have 18 kilograms of water, it's also a mole. Of course, we might use the word pound mole or kilomole just to keep track of the units. But again, the number of moles is just the equivalent number of molar masses. Okay. So I could actually write that down. I mean, the number of moles is just going to be the mass over the molar mass. So the number of moles of component I is just going to be the mass of component I over the molar mass of that component. So mass over mass per unit mole. Well, mass cancels. We're just ending up with the number of moles. So this is another thing that one should just note. And these equations can be modified. I mean, there's different ways to write this. Often we just write this as mi is just equal to the number of moles times the molar mass of component I. Now again, these are hopefully obvious equations, but still I need to write them down. Let's also note that since we're dealing with fractions here often, the sum of the fractions have to equal 1, right? The total number would be just 1. So another note to add to this list is that the sum of all the various mass fractions of the various components I, well, that's going to have to equal 1. And then similarly, the sum over all the mole fractions, and the mole fractions are y sub I. Well, this too also just has to equal 1. Okay. So again, just lots of terms, lots of notation. Let's continue. One thing that we're interested in when we deal with mixtures is finding the molar mass of the mixture. Another thing we're interested in is finding the gas constant for a mixture. I mean, after all, when we're analyzing ideal gas processes, if we're looking at a pure substance, well, we'd often need gas constant data or molar mass data for that pure component. Well, we have mixtures, we're going to need the same kind of data, right? We're going to have to find a way of calculating the molar mass of the mixture as well as, well, the gas constant for the mixture. So we would note that a mixture doesn't actually have a molar mass. I mean, technically a molar mass deals with an individual component, right? A pure molecule or pure atom of some sort. But we can still calculate what we would just call the apparent molar mass. Sometimes it's called the average molar mass. So for a mixture, we need the apparent, or again, we can call it average molar mass. Okay. And this molar mass is just going to be m sub m. Okay. So if we have this particular molar mass, then, well, let's look at some equations here. So first of all, we know that the molar mass is just the mass per unit mole. I mean, it's the same general equations that we use for an individual component. Up here, we're going to use them again for a mixture. So here we would just simply note that the molar mass is going to be the ratio of the mass of the mixture to the number of moles of the mixture, right? I mean, those are the appropriate units, mass per unit mole. This is our molar mass. Okay. So now we can fiddle with this equation a little bit. We would note, of course, that the sum over all the components of the individual masses is going to have to equal the mass of the entire mixture. So we could just sub that in above here. So we're going to substitute that into the numerator. Furthermore, it might be noted that as we sum over all components I, the mass is just the number of moles times the molar mass. So we can also just write this as Ni times Mi. I'm just subbing in this particular equation here, right? And then divided by N sub m. And then we might simply note that we can relate the number of moles to the number of moles of the mixture. Well, we simply call that the mole fraction, right? So this can then further be simplified into simply the sum over all I of Yi times the molar mass Mi. Okay, so this is how we would often find the molar mass. We would know the molar mass of each component. We would know the mole fraction of each component. And then through the means of summation, we're able to find the average, or again, the apparent molar mass for the mixture. Okay, so again, this is an equation that's going to be of some use to us. Also, since we're going to be interested in the gas constant, well, we know that the gas constant is simply going to be the universal gas constant divided by the molar mass. Well, for a mixture, it's going to be the universal gas constant divided by its molar mass. That is the molar mass of the mixture. So R for the mixture is just the universal gas constant divided by the molar mass of the mixture. So here's another equation that's going to be of some use to us. In fact, I'm just generating all these equations right up front, and then we'll start looking at them and trying to see how to solve problems. Let me also note, again, even before I'm done with all this, that there are lots of different ways to solve the various problems that are going to be given to you. You can see already that there's a zillion equations that relate all the different variables that we're interested in. So, there's not always just a single correct equation to use. Sometimes there's multiple equations that'll give us the same results, and we'll get a feel for that as we start looking at examples. Anyway, so let's just continue here. Another thing that we're interested in is relationship between the mass fractions and some of the other terms that we've already looked at. So I'll just write furthermore. Let's say we're interested in some other equations for the mass fraction of a particular component I. So, well, again, we know this is just the ratio of the mass of any particular component to the mass of the mixture. We would also note that mass is just the moles times molar mass. So we can write this as Ni, capital letter Mi, so moles times molar mass of I. And then in the denominator, we know that this is equal to, well, as it says over here, this is just the number of moles of the mixture times the apparent molar mass of the mixture. So this equation certainly holds. And then furthermore, we would note that Ni over Nm is simply the mole fraction. So we could just write this as Yi and then times the molar mass of component I divided by the molar mass of the mixture. Or sometimes what we do is we just rewrite this and express it in terms of the various variables that would allow us to find the mole fraction. So we could just rewrite this, and Yi is therefore going to be the mass fraction of I multiplied by the molar mass of the mixture, and then simply divided by the Mi term. So the molar mass of each component. So here again is another equation that we have that relates the various terms of interest to us. So honestly, this is the basic equations we're going to need. It's not all the equations. There's others that we'll develop shortly. But we now have on the board most everything that we're going to need as we either do our gravimetric or a molar analysis. Now, there is an example problem in your book. I believe it's 13.1, which basically shows you, one type of example problem. Please read your textbook as it deals with mixtures. There's lots of really good examples in there. And again, there's various ways to solve the same kind of problem using different sets of equations. So it's good to look at these different examples. So let's just begin with, well, not begin, let's just continue with an example problem. Now, this one is actually in your textbook, but I think I've realized that it takes me longer just to figure out how to use that darn computer and the overhead system than just writing it on the board. So I'm going to do it this way. Here's problem 312 from the 8th edition, which is, of course, your edition of the textbook. What we want to do is find the mole fractions of a gas mixture that consists of 75% CH4, which is methane, and 25% CO2, which is, of course, carbon dioxide, by mass. Okay. We also want to determine the gas constant for the mixture. So this is the first problem that we're going to deal with. Now, I might note, as we look at this problem, that they haven't actually given me the mass of the two components that make up this mixture. All they've really done here is given me the mass fractions of the two components. Now, sometimes when you're given a problem like this, that is, where you're given percentages, whether they're mole fractions or mass fractions, sometimes we use a device, if you will, for solving the problem. We just assume that we have 100 of whatever the percentages are that we're given. So for instance, we're given mass fractions here. Let's just assume that we have 100 units of mass, whether it's kilograms or pounds, it doesn't matter. Let's just use kilograms here. So let's just assume we have 100 kilograms of mixture. So this is how we're going to begin this problem, just by making this particular assumption. Now, in doing so, we could pretty easily find our mole fractions. We would note that having assumed 100 kilograms, well, if 75% is methane, then that means we have 75 kilograms of methane. And it also means that we have 25 kilograms of carbon dioxide. Okay. And now that we have these, we should be able to find the molar masses just by going into our tables. And once we have the masses and the molar masses, we can just apply, well, one of these equations over here. I don't know, how about that one? And we can find the number of moles. And once we know the number of moles of each component, then it's pretty easy to add the two numbers together, find the number of moles of the mixture, and find the fractions that they've asked for. So it's not really that complicated of a problem, but it's different than anything you've seen. So first we're going to have to go into our tables. And table A1, A2, I think, actually. In table A2, we can find data for various gases. It might be A1 or A2. I'll just put a question mark. I don't remember which one. But nonetheless, we're going to need our molar mass data. So that's probably the first thing we want to do is just get our data. And for methane, the value is 16.0 kilograms per kilomole. And for carbon dioxide, it's 44.0 kilograms per kilomole. So there's the mass data, the molar mass data that we have. And now we can find the number of moles of each. So the number of moles of methane is just going to be, well, the mass divided by the molar mass. So this is the mass divided by the molar mass. And that's data that we have, right? We have the mass of 75 kilograms. We have the molar mass of 16 kilograms per kilomole. So we're just taking the ratio of the two. And clearly that's going to give us the number of moles. So that's going to just give us 4.688 kilomoles. And then we do exactly the same thing for the carbon dioxide. So we got 25 kilograms divided by 44 kilograms per kilomole. And that's going to give us 0.568 kilomoles. Now we could just sum the two together to get the number of moles of mixture. So we just throw those two numbers together, and we get 5.256 kilomoles of the mixture. And now we can find our mole fractions. So the mole fraction of the methane is the number of moles of the methane over that of the mixture. So just use the data above 4.688 divided by 5.256. Both of these are in kilomoles. So clearly the units cancel. And we get a dimensionless fraction, which is what we want, of 0.892. You could always write these as percentages if you want to. Not necessary, but if you want to, you can. And then similarly, for the carbon dioxide, we just divide its number of moles by that of the mixture. So again, take the numbers from above, 0.568 divided by 5.256, and that's going to give us 0.108. Okay. Now, again, we could write this as a percentage if we want to, but not necessary. By the way, you could have found this mole fraction of CO2 just simply by recognizing that since there's only two components in the mixture and they have to add up to 1, we could just subtract 0.892 from 1 and we still get 0.108. So, it doesn't hurt to just make sure that at the end that the sum of the two actually does equal 1. By the way, I did it this way because sometimes you'll have problems with 3 or 4 or 5 different components. You can't find the first component and then just subtract it from 1. I mean, you're going to have to do this for all the components, well, except for perhaps the last one. The last component you analyze, well, then you can just subtract from 1 the previous number of mole fractions and you'll get the right result. But nonetheless, this gives us the mole fractions. And then the next step, in order to find the gas constant for the mixture, we just have to divide our universal gas constant by the molar mass of the mixture, which means we need the molar mass of the mixture now. So the molar mass of the mixture, we know that's just the mass over the number of moles. At the very beginning, we assumed that we had 100 kilograms of the mixture. And based on 100 kilograms, we end up with the 5.256 kilomoles. So we can find the molar mass as 19.03 kilograms per kilomole of mixture. By the way, another comment. If you don't assume 100 kilograms, that's okay. You can assume anything you want, really. If you assume 1,000 kilograms or 1 billion kilograms or 2.5 kilograms, all your masses are going to be proportionally changed. Your molar masses, of course, are the same. Your number of moles, of course, are going to be different now, but you're going to still end up with exactly the same mole fractions. That's not going to change at all. And your molar mass is still going to be the same. I mean, everything is proportional. So, we use 100 as a device. We're just using it because it simplifies the mathematics. But, you can choose any mass basis you want. Still, we now have our molar mass of the mixture. And now our last step. We just divide our universal gas constant by the molar mass. So, of course, we're going to have to go into the inside back cover of our textbook and find the appropriate value of the universal gas constant using the proper units. This is just 8.314 kilojoules per kilomole per Kelvin. And the molar mass is 19.03 kilograms per kilomole. So kilomoles cancels. We do our math, and we end up with 0.437. So 0.437. And the units are kilojoules per kilogram per Kelvin, which, of course, are the correct units for the gas constant. So there's an example problem that shows how to use this. Yes?
So at the beginning, we picked our own mass in terms of kilograms, and so all our answers are now in the SI system. Is it just as correct, for the sake of doing homework and everything, if we arbitrarily picked the English system?
Yeah, in fact, most of the problems are going to give you some information so that it's clear whether you should be using the SI or the British units. Okay. So it should be pretty obvious. If it doesn't say anything at all, then you can use any set of units you want. But usually there's some clue somewhere in the problem statement.
Okay.
Okay. And you might note also that for problems identical to this one, sometimes you may actually be given the mass. I mean, it's not like you're always given just a mass fraction or mass percentage. Sometimes you know the actual mass of the components, and then you can just kind of start the problem from here. You get exactly the same results. So, any other questions or comments on this? All right. So the next thing that we need to do is, well, we don't need to do this. Let's do another example problem. So this one is not in your book. Let us find the molar mass and the gas constant for air. And let's be given the mole fractions of the two primary components in air. The mole fraction of oxygen is 0.21 or 21%, and the mole fraction of nitrogen is 79%. Okay. So we've seen these numbers before, at least we've heard these numbers, and I think we all know that 21% of our environment, more or less, is oxygen, and the other 79% is nitrogen. Now, as you've heard those numbers before, you might consider that, wait, aren't those volume percentages? I mean, when we talk about 21% oxygen, doesn't that mean 21% by volume? Yes, it actually does, and one thing that we'll see either later today or on Wednesday is that mole fractions do equal volume fractions for gas mixtures. But nonetheless, let's just continue with this problem. So we want to find the molar mass and the gas constant for air given these two mole fractions. All right, so it doesn't sound like too hard of a problem. We know that the molar mass of the mixture is just going to be the sum over all components of the mole fractions times the molar mass of each individual component. And of course, finding R, just like the previous problem, we would just find the mixture as a universal gas constant divided by the molar mass of the mixture. Now here I could write the word air instead of mixed, or instead of M for mixture if I wanted to. I'm just going to leave it in terms of these general equations. So quite frankly, there's not a whole lot to really do in this problem. We're going to sum these fractions, so 0.21, and then times the molar mass associated with oxygen. So this is 31.999, and this is going to be kilograms per kilomole. And then we add to that 0.79, and then the molar mass for nitrogen is also listed as 28.013 kilograms per kilomole. And again, I don't recall off the top of my head whether it's in A1 or A2, or it may actually be in both. So again, I'll just put a question mark, but you'll be able to find these data. All right, so we just do our math. And what we end up with is 28.85. And the units are kilograms per kilomole. And there would be a calculation of the molar mass for our mixture, which is nominally air. And then we do the same thing as previously. We just take our gas constant, so 8.314 kilojoules per kilomole per degree K, and divide by 28.85 kilograms per kilomole, and we end up with 0.288 kilojoules per kilogram per Kelvin. Okay, so there's just another example. Now, you may wonder, well, why did I pick such a simple little example? And the reason is because that data doesn't seem to be the same as the data that's in the appendix of your textbook. Keep in mind that in your textbook, they've taken this wonderful gas mixture that we just call air, and they've assumed it was a single component. They basically calculated in the tables the molar mass, the gas constant. You have data for heat capacities, specific heats, et cetera, et cetera. You may wonder, therefore, well, why these numbers are different than the numbers that are published in the book. Well, it really has to do with the assumption we made here at the beginning. Is air really 21% oxygen and 79% nitrogen? That's the proper proportion of oxygen to nitrogen, sure, but that's not the only thing that's in air. Even if we ignore the water vapor in the air, we would use the phrase dry air if we're only dealing with the air components, not including water vapor. But nonetheless, we've excluded all the other gases that are in the air, right? I mean, I'm not even talking about the various pollutants and carbon dioxide and all of that, but what about other gases that exist naturally? There's a lot of them, right? All the noble gases, xenon, neon, argon, etc. You've got other gases like radon gas that exist in nature. So there's fractions of these gases up to close to 1% in the air, and those are not being considered in this particular calculation. However, when you consider air in thermal property tables, yeah, you would generally utilize the air data based on all the components that are in the air, and that's why your number is going to be a little bit different. This will be closer to like 28.97, something like that, as far as the molar mass. The gas constant is going to be 0.287 instead of 0.288. So certainly we're going to be close, but we're certainly not going to be identical. Nonetheless, that was really the purpose of this particular example, just to make sure that you understood that not all the numbers we read in our tables are completely accurate or completely make sense based on our understanding of the real world. So again, these are just some basic examples. There's a lot more in your book. So once again, our approach is to find mixture properties based on the properties of pure substances. Now, it turns out that we don't quite have enough information yet to solve all of our problems. And as such, there are a couple of rules, or we call them laws, that are in place that we're going to have to talk about now. And these are called Amagat's law and Dalton's law. More specifically, Amagat's law of additive volumes and Dalton's law of additive pressures. So we're going to look at these two laws. These are basically observations that have been made and then experiments done in a lab somewhere. And these rules were basically proven to be accurate. So let's look at these two. So again, with the understanding that we're only dealing with ideal gases here. And quite frankly, these laws are specifically set up for ideal gases. By the way, nothing in anything that we've done up until this point specifically requires that we're assuming that the gases are ideal gases. Everything we looked at are just general relationships, right, between masses and moles and mass fractions and mole fractions and molar masses and gas constants. There's nothing that says it has to be an ideal gas to go through any of these problems. I mean, granted, we're looking at gases and we're using gas constants, so clearly we're talking about gases, but the general relationships are just general relationships. These laws, Amagat's law and Dalton's law, specifically apply only to ideal gases. So let's look at these. So two laws of interest. So here's the first one, Amagat's law of additive volumes, additive pressures. No, Dalton's law, additive volumes. Amagat's law, I'm doing it again. It is volumes. Okay, I should just read my notes and stop talking. So Amagat's law of additive volumes. So what's kind of odd about gas mixtures, and that's really what these two laws are all about, is that when we're trying to find thermodynamic properties for the various components in a mixture, it turns out that some of these properties behave in a way as if they existed alone without the other gases present in that mixture. Okay? So what Amagat's law basically tells us is that we can sum together what we would call the component volumes, that is the volumes that would exist if that component existed alone in that volume. We will just simply sum together all of these component volumes, and together they will add to the total volume. So let me actually write that out. Hopefully it'll make more sense as it's written down. So we have a mixture volume that we call Vm. And what Amagat's law basically tells us is that the mixture volume is going to be the sum over all the components I of VI. VI represents the component volumes, but at the same temperature and pressure of the mixture. In other words, if each component existed at the temperature and pressure of the mixture, we could find the volume of that component. And then we just add together all the volumes of these components, and that's going to give us the mixture volume. So this is just a law. Again, this is something that's been proven in labs and never been able to be disproven to the point where we just call it a law. But nonetheless, this is our mixture volume, where VI is called the component volume. Basically, this is the volume that component I would have if it existed alone, again, not as a mixture, but as if it existed alone at the temperature and pressure of the mixture, Tm and Pm. So the mixture volume is the sum of the component volumes, and the component volume is the volume that that gas would have if, again, it existed alone at the same temperature and pressure as the entire mixture. Okay, this is just simply something that we find, and there's the basic equation. Now, we will note that we're talking about ideal gases, so I'm going to continue this and develop some new equations from that law. We know that for an ideal gas, PV equals nRT. So we'll just write this as the number of moles of component I are just going to be PV over R universal times T, right? That's just the ideal gas equation of state. And we'll note that since the number of moles of the mixture is just going to be the sum of the number of moles of each component, and since we know that based on this particular definition of the component volume, we know that the temperature of component I is the same as that of the mixture, so Ti equals Tm, and we know that the pressure of each component, Pi, is going to be equal to the pressure of the mixture. Then what can we find? So I'm just going to plug in some information into my ideal gas equation. So back to this equation for so what would be the number of moles of the mixture? Well, again, we're going to sum over all components I, but Ni is PV over R universal Ti. So I'll write it as Pi Vi over R universal Ti. Okay. Then we would again note that the component has the same pressure as well as temperature of the mixture. And we would also note that the universal gas constant is just a constant. So those could actually be pulled out of the summation, and we would have Pm over R universal Tm. And then all we're really left with is the sum over all I of Vi. However, we know that the sum of the component volumes is equal to the mixture volume. So this is just going to be Pm Vm over R universal Tm. And, well, we have the ideal gas equation of state now being proved for a mixture. There was nothing that said that the ideal gas, well, at least nothing we've dealt with, that said that a mixture of ideal gases also behaves according to the ideal gas law or ideal gas equation of state. But basically, we've just proved that it's true. So the ideal gas equation essentially is going to hold for the mixture as well as for the individual components. So this is another equation that's going to be of significant use to us. Another thing that one might note, we're often interested in the ratio of volumes, the volume of one component to the volume of the mixture. And we can now apply the ideal gas equation of state both to the component as well as to the mixture. So we can just write this as Ni R universal Ti over Pi in the numerator. And then the ideal gas equation essentially from directly above. So Vm is going to be the number of moles of mixture, R universal times the temperature of the mixture over the pressure of the mixture. Okay. But again, let's recognize that according to what we're covering in Amagat's law, the temperature of each component is the same as that of the mixture. The pressure of the component is the same as the mixture. So basically, Ti and Tm cancel, Pi and Pm cancel. Of course, the gas constant is going to cancel. So we simply end up with Ni over Nm, which of course is just our mole fraction, right? So this equals Yi. Now this equation I'm going to call equation 1 because I'm going to refer to it later. So this comes directly from Amagat's law of additive volumes. Now, why is this important? Well, this tells us that volume fractions for ideal gases equals mole fractions. In fact, that's what I just mentioned a few minutes ago with regards to air, right? I just kind of mentioned it in passing at the time, but now we recognize that it's indeed true. If we can figure out the mole fractions, they're going to be the same as the volume fractions. So again, this is important. So again, mole fractions equals volume fractions. I have just abbreviated fractions. Hopefully you'll understand that. So nonetheless, this is one of the laws associated with ideal gas mixtures. The next one is called Dalton's law, and it's actually similar. This is called Dalton's law of additive pressures. Right? So here what we're going to do is something similar. First of all, we're just going to identify something called the mixture pressure, or PM if you will. And just like we did for volumes over here, we're going to note that in the same way that according to Amagat's law, the volume of each component behaves as if it existed alone at the temperature and pressure of the entire mixture. For Dalton's law, we say much the same thing, that the pressure of the mixture is actually going to be the sum of the pressure of the individual components. And these individual components will exist as if, these individual components will have a pressure that corresponds to the assumption that that individual component exists alone at the temperature and volume of the mixture. So it's the same kind of thing, it's just essentially replacing volume with pressure. So Dalton's law, the pressure of the mixture is going to equal the sum over all components I, and then Pi. And again, that pressure would assume that it would be at the same temperature and volume of the mixture. Okay, so let me write it in words, just like I've done over here. So first then, where Pi is called the component pressure. Okay, and again, this is the pressure that component I would have if it existed alone at the temperature and volume of the mixture. And again, the temperature and volume of the mixture are just Tm and Vm. Okay. So this is simply what we observe. okay, we observe that if we were to take the pressure of each component as if it existed alone in the entire volume and at the pressure of that mixture, and then add together these individual pressures, these component pressures, that sum would give us the pressure of the entire mixture. So again, this is just something that we would observe. Now we're going to do the same thing like we've done over here and fiddle with equations. So first we're going to start with the number of moles of the mixture, and of course we know that's just the sum of the number of moles of each individual component. And again, we will note, like we've done over here, that since Tm equals Ti and Vm is going to equal Vi, we'll now write the equation for the number of moles of mixture. And again, we're just going to basically take the equation from above, which is the same thing that I did over here, right? I just started with this equation here and kind of summed it. But nonetheless, we're just going to sub in first the ideal gas equation of state. So we're summing over all components I. And of course, PV equals nRT still. So this is just PI VI over R universal times TI. Again, recognizing that according to this law, each component has the same temperature and volume as the mixture. So it's going to be the same for each component. So we're going to pull out the V term. So this is just going to be Vm, again, the same as the entire mixture. R universal and the temperature come out as well. And then all that we're left with is a summation over pressure. So sum over all I of Pi. Okay. And again, we would note that the sum over all the component pressures is going to equal the pressure of the mixture. So this is now Pm Vm over R universal Tm. And in fact, this is essentially the same. In fact, it's identical to what we had found at this point from Amagat's law. So again, the number of moles, again, is proven to be equal to the mixture pressure times mixture volume divided by the gas constant times the mixture temperature. Okay. What I would like to do as well is relate certain ratios. So here, what we would do is look at pressure ratios. So if we look at the ratio of the pressure of component I to the mixture's pressure, well, just like we've done before, we're going to sub in the ideal gas equation. So PV equals nRT. So Ni R universal Ti over Pi in the numerator. And then, again, we can use the corresponding mixtures ideal gas relationship. So Nm R universal Tm over P. This should be volume, not pressure, sorry. This should be Vi over Vm. And again, the volume is the same for each component as it is for the mixture. The temperature is the same. The gas constant is the same. And we just end up with Ni over Nm, which again is just the mole fraction. Okay. So this equation I'm going to call equation 2, and we'll get back to it in a little while as well. All right. So we can see then from equations 1 and 2 that, again, there's relationships between these different fractions. The ratio of the component pressure to the mixture pressure is equal to the mole fraction. The ratio of the component volume to the mixture volume is equal to the mole fraction. So I'll just write these both as Ni over Nm. In other words, they both equal the mole fraction Yi. And we can actually rewrite this one more time and put them into the form that we generally see them. And we just end up with Pi equals the mole fraction times Pm. And the component volume Vi is going to equal the mole fraction times the volume of the mixture, Vm. So these are just equations that we typically would see. I might note that even though technically Pi and Vi are called the component pressure and component volume, sometimes they're given a separate name or a different name. Pi is sometimes just called the partial pressure. And Vi is sometimes called the partial volume. Okay. So, yes, these are the component pressures and volumes, but you'll see all over the place these different, these different notations or different terminologies, I should really say. So partial pressures and partial volumes are often the word that we utilize. Okay, so any questions at this point, moving ahead? All right.
Yeah, one kind
Yes.
of conceptual question.
Okay.
So pressure of the mixture equals pressure of the components,
Mhm.
sum of that. How does that math actually work? Can you just like add 14 kilopascals to 20 kilopascals, or?
Well, yeah, I mean, if these are all just pressure data, as long as you have an appropriate set of units, yeah, they could be in kilopascals, they can be in PSIA, it really doesn't matter.
Is it just that simple that like if you got the different components at different pressures, you can literally just add the pressures together?
Yes? Mhm. Yeah, and again, you're using this device, right? You're assuming that each component behaves as if it existed alone, either at the temperature and at the volume of the mixture, or at the temperature and with the same pressure as the mixture. That's just how we find this works. Okay. So how about one more example problem? Any other questions before? Okay. So this example, let's see, it looks like this one is in a previous version of the textbook. Once again, it's going to take me longer just to get that whole system up and running. These are pretty short problems, so let me just give you another example directly. So this is 13.29 from the 7th edition of your particular book. And basically it says the following. We have a rigid tank, and this tank contains a half of a kilomole of argon and 2 kilomoles of nitrogen, that is N2 gas. By the way, argon is just a monatomic gas. It just exists as an individual atom, whereas nitrogen doesn't exist as a monatomic atom in the environment, right? Elemental nitrogen is incredibly reactive. If you have elemental nitrogen, it's just going to attach itself to another nitrogen or oxygen in the environment. But nonetheless, argon is monatomic, nitrogen is diatomic, 2 atoms per molecule, right? Anyway, so what we're trying to do then is we have a rigid tank that contains this number of moles of these 2 gases, and the whole mixture is at a pressure of 250 kilopascals, and the mixture temperature is 280 Kelvin. Now it tells us that this mixture is heated until we get to a higher temperature. Okay, so the rigid tank contains this at this condition. The mix is now heated to 400 Kelvin. And what we want to do is we want to find the volume of the tank and the final pressure of the mixture. So this is what we're trying to find in this particular problem. So I guess the first thing that we want to do is just recognize that we can use the ideal gas equation of state for the mixture itself now. So we would simply note that if we're trying to find the volume of the tank, well, that's really just the volume of the mixture, isn't it? And the volume of the mixture, well, it's just going to be N R universal T for the mixture over the pressure of the mixture. Okay. Now, We can't find this at the final thermodynamic state, but we can certainly find it at our initial state that's been given. I mean, after all, we're given the initial temperature and pressure. We're given the number of moles of each component, so we could certainly find the number of moles of the mixture. We can look up the universal gas constant, so we should be able to find the volume of the mixture at the initial state. So let's do that first. So at the initial state, and of course it's a rigid tank, the volume is going to be the same at the final state, but still we would have the number of moles of the mixture, which is just the sum of the moles of argon and nitrogen, and then times universal gas constant, and then times temperature, and divide by the pressure. So let's just plug in the numbers. So Vm equals, and here we just have a total of 2.5 kilimoles. And then the universal gas constant is the same. You know, it's going to be the same number we're going to use in all of our problems. So 8.314 kilojoules per kilogram per Kelvin. I'm sorry, per kilomole, not kilogram. Per kilomole per Kelvin. The temperature is given in Kelvin, so 280 Kelvin. And then the pressure is given as 250 kilopascals. So again, it's just really a matter of going through the mathematics. Again, it would appear that the units aren't going to work out properly. Certainly kilomoles cancels, but I don't see any meters units anywhere. But they exist, right? I mean, we do this all the time. Kilonewton per square meter is a kilopascal, and a kilojoule is a kilonewton meter. And you know, now you can see that everything cancels out appropriately except for volume units. So we go through our math, and we get 23.3 cubic meters. So that's the volume of the mixture, which is the volume of the tank. Now the question is, how are we going to go through this process? We really haven't even talked about any individual thermodynamic processes. What equation might we even use? Well, as it turns out, we don't need to go through the whole process. We just simply need to use the following relationship. In fact, the relationship we're going to use is the ideal gas equation again. We know that PV equals RT, and this would apply at the initial point, and it would apply at the final point, right? I'll just use 1s and 2s to represent initial and final. And by the way, I have just the gas constant R rather than the universal gas constant, just so I don't have to worry about the number of moles. We'll just put it in this form. And of course, each of these can now be solved for R, right? R is P1V1 over T1, but it's also P2V2 over T2. Now, of course, it's a rigid tank, so the volume is constant. It's the same on each side, so that just cancels out. And therefore, we can find the final pressure simply by using what remains of this equation, which is nothing more than the temperature ratio and the pressure at point 1. So this is just simply going to equal T2 over T1 times P1, right? And that we have. We have all this information. We're told that the final temperature, which is after it's been heated, is to 400 Kelvin. The initial temperature was at 280 Kelvin. The initial pressure was at 250 kilopascals. So again, simple mathematics. We get 357.1 kilopascal. So in this particular problem, even though it sounded quite a bit harder because it kind of implied some sort of thermodynamic process, and well, in fact, there is a thermodynamic process, we would actually utilize equations that are really quite simple and straightforward. Eventually, actually, next time we're going to start talking about individual processes, you know, where we are interested in things like work or heat transfer. You know, we're going to need to find internal energy changes or enthalpy changes, but again, that'll be next time. So.